anything. So
Okay, so hi everyone. I suggest that some people are still coming, but I suggest we can start now. So today we have the second lecture about quantitative spectroscopy, which will be given by Carlos Martínez-Sebastián. So he will talk about from radiative transfer theory to stellar atmosphere codes. So a lot of stuff that we will have to go through. So Carlos is currently a PhD at the Instituto de Astrofísica de Canarias, and he did his master in the University of La Laguna. The topic of his PhD is abundances in galactic O-type stars to study their origin in an evolutionary context. And I would like to say that is will graduate sometime beginning of 2027. And I would like also to advertise a paper that has been submitted. So please please stay tuned. And the paper is Nitrogen Abundances in Galactic O-type stars, further hints for separating binary interaction product from effectively single stars. So I'm really looking forward to read this paper once accepted. So Carlos, if you're ready, then the floor is yours.
Okay, thank you, Sophie, and thank you everyone for being here, and also, well, Sophie and Joe for the opportunity of giving this talk, and I will join Artemio to the thanks to the knowledge for supervising this talk, which is, as Sophie said, a huge topic, a lot of things to talk about. I try to summarize a course that for me was a semester in the master into 40 minutes, more or less, maybe slightly less. So it was a challenge to me, but I accepted. So, as Sophie said, we are in the block 4 about quantitative spectroscopy of massive stars. And I want just to briefly summarize what quantitative spectroscopy is about, which is, or what is the technique? It's about getting some numbers from the star to understand their physics. But to do so, we start with the observed spectrum, and we use also a synthetic spectra or a grid of synthetic spectra. And the idea of quantitative spectroscopy is basically compare observations with synthetic spectra to get some numbers, get the stellar parameters. Here is an oversimplified version, I want to say, because I'm using, or to give an idea, one line, but we need many lines. We need to fit and compare many lines with the idea, for example, to get a temperature, we need to play or do an interplay with the ionization balance. So we need more than one ionization state. One ionization state. It's not only valid. With one line is not enough. So about this, the observations were already presented last week in the first lecture of this blog by Gonzalo Olgado. The comparisons and how to get the parameters will be presented in the third lecture in a few weeks that I invite you to join also by Eugenie. And today I'm centering in here, in getting the synthetic spectra. But I want to punctualize something. As you can see, or you can imagine from this picture, I'm coming from this side. I'm an observational astrophysicist. So this is even a bigger challenge to me to remember all about the theory. Why? Because when we are talking about synthetic spectra, or when we want to get this synthetic spectrum, what we have to do is to construct a model of the atmosphere and then follow what's happening in this atmosphere to get this spectra. So the first thing we need is an atmospheric models or our atmospheric models. But here I want to highlight those are models. And whenever we are talking about models, as an observational, I like to remember what George Box quote, who said that all models are wrong, but some are useful. Because models are not nature. So models are about oversimplifying nature and include the most important ingredients to reproduce them. So whenever we are talking about models, it's very important that we don't use them blindly. we need to understand what we are including, what we are accounting for, because if an ingredient, important ingredient is missing, we will not get models that are able to reproduce nature. So the second part about quantitative spectroscopy of massive stars, of course, is massive stars. We have already talked about this quite a few times during these lectures, but I will use the same classical definition as was already presented in the second lecture of the first block, for example, which is that massive stars are stars that can undergo a core collapse. That's it, classical definition. Those are stars over more or less 8 solar masses. Now the picture is slightly different, but I will not enter in that because I just want to use it to talk about the structure of the star itself, which has, well, and among them, there are different types. I will center in the OB stars, which are those stars at the beginning of the evolution. But in future lectures, hopefully we will also talk about B supergiants, zero supergiants, luminous blue variables, dwarf riots. In this talk, in this presentation of the atmosphere of massive stars, I will be referring to massive stars as basically OB stars. That has a particular structure. Namely, they have a convective core and a radiative envelope. And on top of this envelope, there is this thin layer that is the photosphere, which is the most interesting part for us as spectroscopists, because it's where the light can already escape, as Gonzalo already presented last week. So basically, it's where the spectra comes from, let's say. And the idea of to construct a synthetic spectra is follow the light ray through the atmosphere and see what happens to the light. Okay, these atmospheres have 3 main characteristics that I want to highlight. They have low density, intense radiation, and intense winds. And because, especially of that last point, we need what we call the unified models. So we need to consider the photosphere and the winds at the same time. We cannot neglect them. And to follow the ray, basically, we will try to solve this beautiful equation. That looks pretty simple, but it's giving us how the intensity changes as a function of the emissivity and the opacity. So basically, it's giving us how the intensity changes as a function of the interaction of the matter, the media, with the light. So how we absorb the light and how we emit the light. Okay, so let's see some considerations that we have to do. The first thing that we have to understand, or we have to consider and put our model in, is, okay, so we want to follow the ray. So what is the geometry that we will consider to follow this ray through the atmosphere? I will center here just in 1D and 3D models. 1D models are the simplest case that we can consider. So the simplest among the simplest is the plane parallel case, in which basically we have that the atmosphere is very thin, at least compared to the stellar radius. So we can consider that each layer of the atmosphere is totally parallel to the next one. So basically the angle that the light ray forms with the normal to the layer doesn't change. Then we can neglect this term, and the radiative transfer equation will only be dependent on the angle, but will not change, and on the depth in the atmosphere. This is normally valid for high gravities and low density winds. So if we consider stationary atmospheres, this is the form that the radiative transfer equation takes. That's the simplest. Yeah, it depends on the angle, but it does not change with the angle. Here, I want to just stop 1 second because I already referred to the stationary atmospheres. And I think it's important to remember that stationary atmospheres are atmospheres in steady state, which are time independent. So that's the reason we don't have here the time dependence term. Okay, something slightly more complicated for extended atmospheres is the spherically symmetric geometry, in which we put some layers on top of each other in spheres. And in this case, we cannot assume that the angle does not change through layers. So this angle will be different to this angle. And this angle is different to the normal. So in this case, where even if we consider stationary atmospheres, we will have to include a term that is dependent on the angle. So we will have to include this derivative. We are adding a new degree of freedom. And in 3D models are the most complete. We do hydrodynamic simulations, which are computationally very expensive, but at the same time, very useful to investigate inhomogeneities, rotation, and polarization. And in this case, the radiative transfer equation basically has the full form. That's the reason it's computationally so expensive, because we have too many degrees to solve this equation in too many dimensions. We have increased the dimensional space to solve the equation. Okay, so now we know our geometry. What is the structure in this geometry? So basically, in that case, the first assumptions are that the atmospheric plasma behaves as an ideal gas. So the equation of state takes the form of the ideal gas. And the second strong assumption is that the velocity distribution is a Maxwellian velocity distribution. And I said that this is very a strong assumption because, as you may know, the Maxwellian velocity distribution is valid for an infinite number of particles, which at the deepest part of the atmosphere could be considered approximately true. But as far as we are going to less dense parts in the outer parts of the atmosphere, this assumption starts to be not so accurate, let's say. Okay, and then we have two equations: the continuity equation, this one in here, and the momentum equation, which is basically the well-known Euler equation. And with that, we will try to understand how the forces balance each other. So how the external forces balance the pressure force. Again, let's go to the simplest case. We consider that there is no velocity, so the forces balance perfectly each other. We are in the hydrostatic equilibrium case. And then the Euler equation just takes this form, which is analytically solvable, and we get to this solution. So that's the density as a function of depth. And we have a term here that is the scale height. It has this form. I would not enter too much into it, but basically is the scale at which the density of, or the pressure, we can easily convert this equation to pressure, decreased by a factor of E. That's it. Not so simple case, slightly more, maybe more realistic, is when we consider a stationary velocity field. In this case, we see that the pressure force does not totally balance the external force. And in a spherically symmetric geometry, we arrive to this equation in here. The interesting point about that, well, we cannot neglect that this is already different from zero. But the interesting point is that when we solve this equation, we arrive to this. So this immediately implies a mass loss. So whenever we have stationary velocity fields, we have stellar winds. And those are basically produced either because the pressure force is winning, let's say it's more important than the external force, or because, as I tried to add in this schema, because we have outer or external force that is going in the outer direction instead of just going in the inner. So here we have the variation of the velocity with the depth in the atmosphere again. Here, Bs is the velocity, the sound velocity in the media. And the interesting again about this equation is that it has basically three terms. So the gravity term, that is telling us, okay, if the gravity term is winning, that's it. We don't have this velocity field. And external force term minus the gravity term, of course, is not considering here, and the pressure terms. So depending on which term is winning, we will have a different type of winds. Here I will direct you to the second block in which we talk for few lectures about winds. But just to summarize, let me use few minutes to remember you the different terms, the different type of winds, classical winds. The first one is when the pressure terms winds, let's say, we have the pressure-driven winds. This is typically from the solar type winds and are initiated by the high temperature corona. But the mass loss that this type of winds are producing, it's pretty low. So they are not so relevant for the evolution of the star. Second type, continuum driven winds. Those are produced by the Thomson scattering in a porous medium, and they are theoretically very relevant for metal poor stars in which other winds are not so efficient, let's say. Dust-driven winds, those together with the line-driven winds, the physics that are governing them is similar. So in both cases, again, it's external force that is governing. This one is important for cool stars in which we have dust, and the photons accelerate this dust, and the dust transfer momentum through drag force to the medium and moves all material. That's it. And line-driven winds, it's produced by the large oscillator strength of line transitions compared to the continuum cross sections and the high luminosity. So in this case, the photons transfer momentum to the metallic lines, yeah, and then through line scattering and absorption, we move all the material outwards. And in this case, this is efficient when the peak of the flux is where the atoms can absorb the photons. Something interesting or particular about these cases are the inhomogeneities. So this wind can be inhomogeneous, so the velocity field is not homogeneous, and this produces some overdensities because of some physical phenomena, and some regions with higher densities or lower densities. This is what we regularly know as the clamping. The clamping numerically is usually treated as optically thin to solve the equation. And however, there are approximate treatments for optically thick winds at specific wavelengths. Okay, this last term, the line-driven wind, is the most interesting for us because it's the one governing in massive stars. And in this case, compared to the pressure-driven winds, I want to highlight that the mass loss is much higher, so it should be considered for the evolution of the star. We cannot neglect those winds. Okay, I will just stop because as I started already talking about some inhomogeneities, I want just to mention that there are other inhomogeneities in the atmosphere. Namely, I want to highlight that we always assume that the atmosphere is totally homogeneous, but that's actually not the case. The atmosphere has convection, has turbulence, has other effects that are moving us apart from totally homogeneity. And I want to highlight two very important effects. I will not enter too much into them. One of them is the microturbulence, which origin it's still unclear, but what we know for sure is that it should be included at least in the 1D models. And what we thought is that it might be related, at least in Cantiello 2011, they said it might be related with some subsurface convection zones, and also the microturbulence. Probably about the microturbulence, I want to say that Alba, in the last lecture of this block, will talk more about this term. So I will not enter too much into it. And similar for the macroturbulence. So this term is also another turbulence term that we should include to reproduce the lines. In this case, the microturbulence is changing the abundance of the star, or the determined abundance of the star. This one is not. But we should include them to reproduce the lines. In that case, again, not totally clear where this is coming from, but might be from radial pulsations or subsurface processes. Okay, I will not enter too much into it, and let's move to the other part, to the energy conservation. So whenever we have our atmosphere, we already have considered the equations. Let's put some constraints. The first of them is, again, for stationary atmospheres, I always will be considering stationary atmospheres, and static. In this case, we have the flux conservation. So the divergence of the sum of the fluxes is zero. That's it. The flux conserves. In radiative atmospheres, this equation can be oversimplified because we can assume that all the energy transport is through radiation. So we only need to consider the radiation term, and the equation takes the form of a radiative cooling minus a radiative heating. That's it. And it's equals to zero. So we can use those equations. Thanks to it, we arrive to the luminosity, and we see that the luminosity is constant. So we can use this to derive the temperature structure. I will just talk about two ways of deriving the temperature structure. One of them is assuming or computing the Rosland mean opacity, which is valid in a thermalized medium. Just to remember, again, thermalization, it's basically when matter and radiation are in equilibrium. That's it, simple. And this is regularly valid at large optical depths, and in plane parallel models, it takes this form. Simple. This is an approximation. Again, the opacity, it should be computed properly, not considering the mean opacity, but then we need, for the exact solution, we need an iterative process. Okay, you choose depending what you want to do. Okay, so we have not yet solved the equation that we wanted to solve. That is the radiative transfer equation. And in fact, I said, no, it's a very simple equation. It's only, it's relating the evolution in the intensity as a function of emissivity and opacity. But we don't know yet what is the form of the opacity and the emissivities. So let's consider all the processes that may happen in an atmosphere, namely free processes, bound-free transitions, scatterings, either Thomson or Rayleigh. Those are the most important, and bound-bound transitions. About the free processes, we have that those terms can be computed with the Einstein-Mean relations, which includes the occupation numbers, or involves the occupation numbers and the quantum mechanic cross-sections. So with the occupation numbers, we will enter later, but just to mention, I will not put the equations in here. Okay, about the scattering, the Thomson scattering takes this form. This is a Thomson cross-section, the density, the electron density. But the interesting part is in the emissivity, because the emissivity is related with this mean intensity. So we can already see that this emissivity needs from the intensity. So we need, again, iterative processes. And finally, about the bound-bound transitions, it takes this form, opacity and emissivity, where we need the Einstein coefficients. We can do complete the redistribution approximation and consider that the emission and absorption profiles functions tend to be the same, are more or less the same, but this is, again, an approximation. Be careful with that. and we need the occupation number density. Okay, again, another intermezzo. The opacity depends on the wavelength that we are looking at, and this is producing an effect. Namely, in an ideal world, the opacity is independent of the wavelength, and then wherever the flux is coming from, we can go through a layer and the flux is going through this layer without any effect on the wavelength. In a real world, we have more opaque wavelengths and some that are more transparent. So this is producing an effect, no? Namely, the opacity tries to go through a more opaque wavelength, cannot go there, so it redistributes to go through this layer in a more transparent wavelength. So this is producing a flux redistribution, but as an effect of this opacity, this is producing a backwarming. So the flux is coming back, it's overwarming our deeper layer, while here we are producing a surface cooling. So we need to consider this effect, the line blanketing, to have the proper structure of the atmosphere, temperature structure. So to include them, we can do it with different methods, the super levels, opacity distribution functions, opacity sampling, but whatever the method is, we need good atomic data. This is especially critical in the ultraviolet or extreme ultraviolet. Okay, now that we have said that, we have here the next point, which are, okay, we already know more or less the shape or how to compute our opacity and emissivity, but we see the next problem. We don't know how to compute the occupation numbers. So it depends. Let's see. In the simplest case, the collisions dominate the plasma, and then we are in the local thermodynamic equilibrium. Locally, things are thermalized and the thermodynamic laws are valid. So the occupation number can simply be computed with the Saha-Boltzmann equation, which has this form. And as I said, here the electron density and the temperature are local terms. We don't need anything else. In other cases, as in massive stars, because nature don't want to make the things so easy for us, we need to compute the occupation numbers through a statistical equilibrium. That's what is called the known LTE, when the collisions do not dominate the plasma. And in that case, the point is that the level, the population of it at any level is related with the population at any other level. So to compute the population at one level, we need to consider all the processes happening between this level and the rest of the level of the atoms. And we do need to consider radiative processes and collisional processes. So about the radiative processes, you can already know that radiative processes are dependent on the intensity field. But this intensity, as we know through the radiative transfer equation, depends on the opacity and the emissivity. And these opacities and emissivities depends on the population levels. And these population levels, again, depends on the radiative processes. So we are already in a loop, which means that the occupation number and radiation field have to be computed in parallel. Okay, so this non-LTE has two extra difficulties compared to the LTE case. Namely, apart from the iterations that we need, the physics. We need much more atomic data than in the LTE case. We need all the information about these collisional processes, which cannot be so well constrained. And about that, again, I will not talk, and I will, again, refer you to the last lecture of this blog, which Alba will be giving in few weeks, more than few weeks. And second problem is the computation. We need computational methods that converge to the correct solution. Normally, we will use either accelerated lambda iterations or complete linearizations. Each of them has its own approaches. Okay, so we already know, we already have our theory, our theoretical atmosphere. How do we do to arrive from this to a synthetic spectra, which is what we really want to compare with our models? So we need an stellar atmosphere code that solves all these equations in parallel, as I said, and gets the synthetic spectrum. Here, I have included a table from Pulse 2009 with some of the codes. I want to say this table is not complete, does not include all the codes. All of these codes are in 1D, detail, surface, and celesty. Those do not include the wind. Those do include the wind. All of these 5 codes can treat the winds at least thin winds. Some of them also thick. And as I said, there are 3D approximations. Phoenix, for example, has Phoenix 3D. There are other approaches that are not properly atmospheric codes, but here I want to mention, for example, SPAMS that is able to reproduce more complex geometries. So normally use any of those codes to reproduce geometrical effects of fast rotators or over contact while solving the radiative transfer equation in 1D to simplify, or emulators, for example, as MAUI, developed by Miguel Urbaneja. But still, I will just center in here in 3 of these codes, namely FastWin, CMFGen, and Power, which are 3 of the most widely used codes in the community. About FastWin, well, all of these 3 codes use spherically symmetric geometry and non-LTE, but FastWin starts by using the electron thermal balance. It's valid for not significantly optically thick winds at least in the optical continuum, but it can treat optically thick clamping in an approximate way. And these 2 lines, I want to say that will soon be outdated. So up to now, what happened is that FastWin computed the explicit elements and the most important lines from background elements in the comoving frame, but the, let's say, less important lines from background elements were computed using the Sobolev approximation. In version 11, that will soon is be released, everything is computed in the comoving frame. So this is an update that it will have. Okay, about the blanketing, FastWin used an approximate treatment that is described in here. And something interesting is that not it used, but yeah, normally when we are using FastWin, for the winds, we give this wind strength parameter. So when you read a paper, for example, from the Jacob, you will see this parameter constantly. Okay, so all of these approximations together with the accelerated lambda iteration method to solve the equations gives an execution time of few minutes. Very nice. In the case of CMFGen, again, spherical symmetric geometry, non-LTE. So in this case, instead of the electron thermal balance, it considers the radiative equilibrium, and it can treat winds of all strength, including optically thick winds. As I said, not all of the codes that we described were able to do so. In this case, everything is computed already in the comoving frame, and for the line blanketing, it used the superlevel approach. And something very interesting about CMFGen, for the purpose in the moment in which it was developed, is that it's able to include the time dependent at the time of solving the equation to study basically supernova. But the counterpart is that the execution time is much larger, it's many hours. Power has similar physical assumptions to CMFGen, including, for example, the fact that, well, all of them use the same physical assumptions, basically. But the Power, used again the radiative equilibrium. Something very particular about Power, and it's important to keep in mind as a spectroscopist, or quantitative spectroscopies is that the effective temperature and the stellar radius are output parameters. Phase wind star effective temperature, for example, is an input parameter. Again, line blanketing is treated with the superlevel approach. And by default, in this model, this is something particular of power. The turbulent pressure is included in the hydrostatic equilibrium. So it gives some differences in the derived gravity when you are using power. About the execution time, it depends. In the standard setup, they use few hundreds of super levels per ion, so the execution time is few hours. But in the case that we want a more complete atomic model, including more lines, more super levels, pardon, we are going to many hours. Okay, so some comparisons. I will base this last part in this article that I found very interesting. So what they did was basically taking 4 stars and analyzing them using different codes, namely CMFGen, power, and fast wind. But not only different codes, but different methodologies, so different approaches. This is related with what Eugenie will be presenting next week. But I think it's pertinent to mention here that in that case, for example, you see that for this star, the reproduction of the lines are pretty nice for all the codes, but you can see, for example, this one in here, this line is overestimated. Here, the same reproduction of the same solution is underestimated. So you may say, okay, this model or this code seems to have some problems, pardon. But this is a fast wind model. So what is changing between this F4, this yellow-brown line, and the rest of them, or the rest of dashed lines, which are also fast wind models, is the parameter determination because of the approach used to determine the parameters. So it's not that the code is inconsistent with others, but the parameter determination is different. In that sense, if we go to a different figure summarizing 2 of the important parameters for those stars, we see this. Namely, the parameter determination is consistent, but it has some scatter. In particular, again, here I want to highlight, yeah, you have here an outlier or here an outlier for this star, but those 2 triangles are fast wind models. So it's not that the fast wind models, the other fast wind models that are also triangles, are in the bulk of the determinations. So it's not something related with the code, but with the approach when determining these parameters. So I think, that the conclusion, it's very clear. Different methods have a scatter in the parameter determination. But this is not due to the code itself, but to the unit choices. In particular, there are 2 things that have a huge impact. The treatment of the clamping. And the second thing, even more important, and again, something for the observational quantitative spectroscopies, is the fitting lines. Which lines are we using to fit and get the parameters? This is an assumption that we are doing, and it's important to consider that. Something that can also affect is the atomic model that we are using, or the atomic data that we are putting in our models. This, in fact, can change the results of the models. But this is not something that it's about the code. It's about the atomic model, something that we can control. And I think this conclusion is very clear. The scatter obtained in this work should reflect the amount of scatter to be expected when blindly combining data from different literature sources. And here, I want to highlight the blindly, because sometimes we want to increase our statistics, so we will go to the literature, we will try to take all the parameters from different sources, and try to compare them, and we will find some scatter. But this scatter is intrinsic. So yeah, we can compare literature sources and to try to increase our statistics, to do some statistics. Yeah. But in this case, and I want to highlight that, blindly cannot be acritically. So whenever we are combining data, we need to be critical. And this is related with the next point, which is, okay, the question would be, now for me, which code should I use? Which code is it better, CMFGM, FastWid, Power, any other? So it depends. It depends basically on your science. It will determine which code to use. But whatever your choice is, please keep track of your assumption and approaches and make them public. So whenever we are comparing them, we can understand the difference that we may find between works, and we can compare the scattering and see what the scattering is expected. So that's it from my side. I let you hear three references just for you to go deeper in the atmosphere modeling.
Okay, Carlos, thank you very much for this excellent overview. Do we have question in the audience? A lot of applause. No question. Please don't be shy. Still no question? I have no question, unfortunately. I think it was extremely clear and I learned a lot of things. I still don't know which code I should use, but Artemio. Yes, Artemio, you can unmute
Yes,
yourself. Yes, thank you.
second.
Yes.
So thank you very much for Carlos for this for your talk and your effort. I have only two small comments for the audience to avoid confusion. The first one refers to the figure in the spherical geometry. Can you show the just to avoid that someone starting in the theory gets confused, the angle in the spherical symmetric plot in this one that you should look at is the angle between the ray, which is the red arrow, and the normal to the surface at the point where the ray crosses the surface.
Yes.
I think the plot is a bit confusing. That's why. And just for people that has not seen it before, and also the second point is in page 11. Yeah, this one. Just also to clarify to people that are new to the subject, we have shown here the Saha-Boltzmann equation, which is the balance between two ionization stages. We still need the Boltzmann equation, which is the balance between levels in the same ionization stage. So we need one more equation. I'm sorry, I didn't realize it when we reviewed the talk. But to be consistent with everything, we need one more equation. Apart from that, I think it's an excellent talk, Carlos. Thank you very much.
Thank you very much, Artemio, for these clarifications. Do we have other question, comments? Joe, I think I see you're unmuted.
No, I just wanted to say you had the question which code you should use. Maybe that's a very interesting question, but it's not so easy to answer. So maybe Carlos can give some comments on this.
That's a difficult question because, pardon. Yeah, that's a difficult question because, as I said, it totally, yeah, it totally depends on your science. Each code has a different approach. So it not only depends on your science, but also in your methodology. So for example, in my case, or in general in the Jacob group, normally we use brute force, or we use great approaches in that sense. Fastwind is amazing because it's very fast computing everything. It's less than 1 hour to compute a model. So to do grids, Fastwind might be one of your best friends. But if you want to treat or to study supernova, you do need to include a time-dependent term. You will need CMFGen. Power is optimized for Wolf Rayet. So it totally depends on your science, on your approaches, etc. I don't think there is a correct answer to this question.
Yeah, but there is something which is really important, and I don't know whether this really came out for the audience who is not so experienced in this, namely that the in a lot of cases, at least as you said, it's not so much the difference in the codes, but in the method. And one of the most important points regarding the methods is actually that you have to be very, very critical when you are using the lines which you are analyzing. So for instance, it is still true that for most, as an example, for most atomic models, most atomic models of silicon, there are specific silicon lines which would perfectly fit with other silicon lines, whereas 2 or 3 which do not fit. So if you would include these 2 or 3, then you would get much larger scatter in the derived results as if you would neglect them. And currently it is not completely clear why these lines are not giving the correct results. There must be something rotten, either with the atomic physics, which I doubt, but with the equilibrium, the atmospheric equilibrium. So these are things one has to be very careful in. The other point, for instance, is if you include in your analysis winds, then you have to have a decent model of the clumping, because when you make different assumptions on the clumping, then you will get out different mass loss rates, and your model has different mass loss rates, and you get slightly different ionization or excitation equilibria. So this is a point one has to be really careful. So only when you would compare codes with exactly the same assumptions, then you could discuss about the difference in the codes. But this is usually the least different, the lowest difference. The other ones are much more important.
Thank you, Joe. Sergio?
Yeah, well, first of all, thank you very much, Carlos, for this very nice lecture. And yeah, I don't have a direct question to you, but I understand that the philosophy of these lectures is also to create a forum for us to discuss other things related to the topic that we are covering. And it's a pity that today Andreas Sander is attending the conference here in Argentina, and I see that Wolf Reiner is not present, or John Hillier. So probably this question is just for you or for Artemio, Joachim. But what about the codes we have? Are we already happy with what we have? And then it's a question of understanding all this, as you are saying, the way we do the metrics or how we implement things related to atomic data and blah, blah, blah. Or you think that in the future, we will need important improvements to be done by the new generation in these codes? Or are we happy enough with these codes, and then the development should go in the line that, for example, John Sundquist is doing the 3D models? What is your impression, or the general impression of the audience? What are the homework for the new generation related to this building of stellar atmosphere codes or improvement?
Well, I can begin if you want, but I think as far as we have things like macro and micro turbulence and things like that, we cannot be happy with our models. So that means we have to keep going on, and probably we need improvements in many areas. As Carlos has said, atomic data, it's extremely important. It's not directly, or to say it's one aspect, but also the inhomogeneities in the photosphere and the wind, and the velocity fields that are the turbulent related to turbulences, inhomogeneities, etc., in the photosphere, which probably will mean that we need 3D in any case, and that means also that we need better numerical methods to be able to treat this in detail. So I think we cannot be happy with our models. We can be happy with the development. I mean, with what we did when we look back to the beginning, we may be happy with what we have. But if we compare with our stars, and we still have problems like from the mass discrepancy to the need of things like micro turbulence, we cannot be happy with them. We need more. We need more realistic models. That's my opinion.
Then in this sense, for example, you think that this approach that sometimes is followed by the Gustar people that we use, because obviously 3D models are very expensive computationally, so use those as laboratories to prepare prescriptions that can be used in the 1D models. Is this a valid approach also in this domain?
Well, I think, in my opinion, the different approximations are valid as far as they are able to reproduce the observation that you are analyzing. That means you don't need to say you don't need general relativity to describe how a stone falls on Earth, but you need general relativity to describe the anomalies in the motion of Mercury. So here is the same. You don't need a very sophisticated model to reproduce the basic features, but to reproduce the details that you observe in many cases, you need better approximations. For example, you don't need LTE to reproduce the photosphere of the sun, basically the spectrum, but you need the 3D models to reproduce the effect, to get rid of the effects of micro turbulence in the sun, for example. So this is the same. You don't need the most sophisticated model for everything, but for the details, for the very fine details, to say that way, you need better models.
Artemio, can I ask you, because someone in the audience is not familiar with that, to explain in a few words what microturbulence is, please?
Well, microturbulence actually is a fake parameter. Actually, it's used to reproduce what we observe. It's introduced like an extra broadening in the spectral lines, but actually the physical meaning of that is very uncertain. I mean, we know it in the sun, for example, where the 3D time-dependent model calculations reproduce the effect of microturbulence, of what we call microturbulence. But for our massive stars, microturbulence has such a large values that this cannot be reproduced in the same way. Now, the first calculations in 3D by the group of John Sundquist point in a similar direction to the sun, but these are still the beginning of it. That's very promising because, I mean, in the sun and in low mass stars, things began exactly that way. First, closed boxes, and then you try to extend more and more to more realistic atmospheres. The problem is that we have to handle non-LTE effects and the coupling of radiation in matter in much more complicated ways than in low mass stars. But microturbulence is probably related to motions in the atmosphere, in homogeneities and motions, and is for us at the moment in 1D, in one dimension, a fake parameter.
Excellent. Thank you very much. Okay, I see, Michael, you have your hand raised, so please.
Yeah, I just wanted to kind of comment on one of the things that Artemio mentioned a couple minutes ago. In that, as long as the models are able to reproduce the observations, then we may not necessarily, then in some cases that can be good enough. But I also think it's important to kind of recognize that there are some times where you can create a model that is able to reproduce the observations, but that model is not necessarily realistic in terms of that there are more effects that are going on, and just because the model can reproduce observations doesn't necessarily mean that the parameters that that model is giving you are the correct ones. So I mean, things like 3D effects, things like rotation in stars. I mean, these kinds of things can bias some of your parameters, and even though you can get a model that reproduces the spectra well enough, the parameters that you get out may not necessarily be correct. So I also think that there's so I agree with what you're saying, but I also think that it's important to kind of for us to move in the direction of trying to figure out where these uncertainties can come up and kind of where we can go wrong, even if we do have a model that looks like it can reproduce the observations well enough.
Yeah, I agree with your comment.
I think it's an excellent comment also. Okay, so I have a request here, Joe. So we would like to have your opinion on improvement needed in 1D models. And we is Sergio, basically, but I'm happy to have it too. So
Yeah, okay, good. So my point is the following. I don't think that at first the models have to be improved too much, because with the 1D models we are somewhat at the end, but we have to test them, and particularly we have to test their connection with the atomic models. So what we are now, everybody is beginning. Some people have already done this a couple of years ago, but in not a really systematic way. For instance, is that we have to analyze and to compare the ultraviolet part with respect to iron. This is one of the important points which has not been done too much, and iron is one of the most important elements. So this is something, and hopefully we will find out that most codes give the same result. What we already know from some work is that we can, as Michael has said, we can reproduce a large part of the spectra. But this not necessarily means that the derived abundances are okay, because particularly in the iron, we have the dichotomy with this, what Artemio said, fake parameter microturbulence. That's very, very strong. One of my very first PhD students, you can imagine, that's a very long time ago. He has made a couple of tests with this, and he found a really strong impact on the iron on the derived abundances. So, and as long as we do not know what this number is, and whether when we, for instance, know the microturbulence from carbon, that would be the same then for iron. As long as we do not know this, it's a very difficult story. So this is something, in my opinion, where we have to work. And the other point is, of course, what Michael also said, Michael Abdul-Masih said, is that we can get a fit with wrong parameters. That's certainly true when we only concentrate on a small part of the spectrum. But there are now, meanwhile, quite a lot stars where we know the spectrum from the gamma ray range to the radio range. And in my opinion, at least, it would be somehow difficult to reproduce the complete wavelength range if with wrong parameters. So when we increase our spectral range, then I would think that these coincidence of wrong parameters giving the same spectra would go down. So this is something which I think needs to be done in the next years. It's not so much, of course, there will be always some changes and improvements in the codes, but I do not see any, how to say, any real big thing until those people as John Sundquist and others from their 3D simulations can show us or can give us some guidance how we might include these 3D effects into our 1D codes. But this will take quite a while, I guess, until this becomes clear. That's my opinion. Thank you.
Thank you, Joe, for your opinion. I think it was also excellent. Sergio, would you like to react on that?
Yeah, so maybe to complement for the people watching this in the future, it's also important, I think, to consider that even from what you say, the models are more or less from the assumptions made in this context are okay, are well implemented, are well coded, and depending on what you want to do, you can use one or the other. But also we need to remember that not necessarily we need to use the assumptions by default in those models, but there are more physics implemented inside that we can modify, and we can also play a bit with this or that, because not necessarily the things that we consider now that are the valid ones will be by default used in the future. But for example, in the case of the turbulent pressure, this is implemented in the codes, even not necessarily we are switching on this option. So go into the codes and try to understand if you can also validate other assumptions for the future. Just for those people watching this in the future.
Thank you, Sergio. Do we have other? Artemio, please.
Sorry, just a small remark. Remember that even if we are able to get indications from 3D models to improve 1D models, for example, as is done in low mass stars, with 1D models, we will not be able to reproduce every details of the spectrum simply because the stars are much more complicated than that. You know? So I agree with Joe that we are close to the end of what we can do with 1D models and need to jump to higher dimensions, to more dimensions.
At least in some way it is remarkable that for specific stars we are already able to reproduce not only the photospheric lines, which is not so difficult, but also that when we play a bit around, that we are able to reproduce various specific shapes of wind lines. This not so much of course on the Pisugni lines, because they look always the same, at least when there is not large rotation, but for the H alpha lines, the infrared lines, and so on. So we cannot be so far away from some pseudo-realistic treatment, I would guess.
Well, I think this is related probably to the fact that if you integrate over the surface, the different inhomogeneities smooth down and are close to an average, which is well reproducible.
Right. And so then the real question is this average, what we are deriving, are the corresponding parameters which are producing this average? Are they far away from reality or not? And this is, a different question.
This can we only know, I think, when we have very realistic models, and then look at as you said, as every single diagnostic point to see whether everything matches. And then we will be able to say whether the smoothed or integrated 1D model that corresponds to this 3D model is actually reproducing the right parameters or not. There is a long way up to there.
Excellent.
Not to introduce binaries.
Yeah, this is
we could. Sergio?
And then a last question also. So I'm aware of the difficulties of solving computationally the radiative transfer equation together with the rest, and that a lot of work was done to try to do the best. But is there a way for improvements of this? I mean, for example, because I remember one meeting, people doing 3D models in cool stars. Is AI helping us in one way to do these computations? Are methods that can be, or this is the best that can be done in terms of the solution of the equation, and really have to live with that? What is your opinion?
Certainly, AI will not help to solve the equations, because this is something which requires some experience and some tricks. But what AI can help us a lot in analyzing the models, of course. This is something which can be really done, and particularly for those, it will help us to increase the computational speed of setting up model grids, because with AI, our model grids do no longer need to be as large as they used to be. So then we can afford of calculating more time-consuming models and doing the interpolation, so to say, in a much faster and more precise way. So I would see this is the importance of AI in the analysis and in the interpolation. Of course, not only used blindly, but for instance, as Miguel is doing this with piecewise principal component analysis or something like this. But anyhow, in this respect, AI will help us. But whether
Because, for
it will
example,
help us with solving the equations, this is certainly not the point. But, and this is something, maybe I'm pretty sure maybe the people will kill me in 10 years when they see this video, but I'm convinced that within the next 10 years, quantum computing will have improved a lot. I'm not sure whether quantum computing is really the way of doing stellar atmospheres. But for instance, if we would switch our radiative transfer to Monte Carlo, as was suggested by Leon Lucy and other people, this is, of course, much more easy to implement in quantum computing. And since the radiative transfer anyhow is the most time-consuming thing, then I would guess that with quantum computing, we can really boil down the computational times considerably, also in more dimensional situations. And that might help.
Because I remember related to that was, I think the proposal was more to deal with the opacities and all this, instead of doing the interpolation and all this, use IA methods to have all the information for the opacities, and this will help also to speed up the process of not to solve the equations.
How shall this work? I don't understand what's the suggestion.
So I understand that when you are solving the equation, you also need to have all the information about the opacities, the different type of. So in this case, in many cases, you are doing interpolations with approximation and all this. So for example, for the line blanketing, it's not the same that you have to provide all the information and all the function and then do interpolation and all this, or if you kind of squeeze all the information give extract the most important. I don't know exactly, like
but AI
needs
AI at first needs the information. Of course, what you can do is you can have a better algorithm to collect the opacities and the emissivities. But of course, somebody has to calculate them at first, because they.
But once you have it, is if you want to have the best will be to have high resolution in frequency of all these opacities. But then this is not possible computationally. So then you kind of decrease the resolution of this. But then with these other methods, maybe you can consider all the resonance lines or all these things in a different way. I don't know. It's something that someone was commenting at some point. But
well, I think that you can ask today AI to write a code, for example, to solve the equations using this or the other method, and the code and the AI will be probably very good in writing more or less well-organized code with well-documented, and you can improve on that, saying, okay, now I need more and more, then please parallelize it, and so that's possible. But if the question is, if we can ask the AI, please write a code using a new method to solve the equations, this is nowadays at least beyond the capabilities of the AI. Whether this is
I'm
in the
not
future
sure
with
at
computing methods, whether with quantum computers this is possible, maybe, but I think today is not yet possible. The method has to exist for the AI to
and
implement it in the code.
I have never seen Artemio AI to couple various subroutines, so to say, and to make a very efficient big code, because we are not speaking here only about one typical partial problem, say inverter matrix or something like this. Of course, this is easy with AI to ask for a code inverting a matrix, but already to write a code which solves the equations of non-LTE, there are different methods, and my fear would be when I leave this to AI that it would use some method which is finally one of the slowest ones, because the result will be very exact, but it will be also very slow because the AI does not know these tricks. Of course, at some point it will, but currently I'm pretty sure that not.
Yeah. Okay. I'm not sure. I think the AI is right now able to do it. Perhaps not immediately, perhaps not without guidance from the user and without corrections later. But I think it's close to that, if not already able to do it.
Okay, then ask it.
No, because probably you need a very good guidance to the AI, and you already have the code, so what's the point?
Okay. Someone wants to comment on that, or something else that has been said so far? From the younger audience, maybe? I didn't say that you're old, right? I mean,
I am.
sorry. Okay. It was a very interesting and long discussion for this talk. It was extremely helpful, I think, and rich. So I don't see anything anymore. So then I maybe suggest, if you're fine with that, that we close this this talk here, and we say thank you to Carlos again, to Artemio, to Joe, and for all the useful discussion afterwards.
Do you know when we have the next talk?
Yes, in 2 weeks.
In 2 weeks.